All right, today we're going on a little journey from the concrete that builds our cities all the way to the frontiers of nanotechnology. We're going to explore the very materials that make up our world and see how they're evolving to actually become intelligent. So let me ask you a kind of weird question. What could a sagging bookshelves possibly have in common with a high-tech smart window? I know, it sounds totally random, right? But the answer gets at a fundamental problem that engineers have been trying to solve for, well, centuries. And that problem is called structural deflection. It's really just a fancy way of saying everything bends. A huge bridge under the weight of traffic, the shelf holding your books, everything. You could say the entire history of building things is really the story of us trying to control that bend. So yeah, this universal bend, this deflection, that's really our starting point. It's a problem we've been tackling since we first stacked one stone on top of another. And you better believe our solutions have gotten a lot more sophisticated over time. For the longest time, the answer was pretty simple. If something bends too much, just make it stronger. The very first solution was all about brute strength, just using materials that were thicker, heavier, and tougher to resist whatever was pushing on them. And that whole brute strength approach, well, it gave us the undisputed workhorses of the modern world, concrete and steel. These are the materials that built our skyscrapers, our bridges, pretty much all of our modern infrastructure. They are the titans of traditional engineering. And we got incredibly clever with them too. We came up with reinforced concrete, which brilliantly combines concrete's strength against being crushed with steel's ability to resist being pulled apart. We engineered steel into I-beams and trusses, these amazing shapes that are super strong for their weight. For more than a century, this was pretty much the peak of material design. But that, of course, brings up a really interesting question. What if the goal wasn't just to be strong? What if we could design materials to have all sorts of specific properties, to be more than just passive, rigid blocks? That question, well, it sparked the next big evolution. And this leads us right into the world of hybrid materials. See, instead of relying on just one substance, engineers started combining different materials to create something totally new, something with abilities that neither material could ever have on its own. We're talking about composite materials. Now, the basic idea is ancient. I mean, think about putting straw in mud bricks. But modern composites take this idea to a completely different level, precisely blending materials to get some really incredible performance. The problem that composites solve is that classic engineering trade-off, right? You might have one material that's incredibly strong, but it's also super heavy and brittle. And another one might be light and flexible, but it's just way too weak for the job. On their own, neither one is perfect. So the solution is to combine them. By mixing strong glass fibers into a light polymer, you get something called glass fiber reinforced polymer, or GFRP. And the result? A material that's both strong and light. This is an absolute game changer, and not just for performance. Lighter materials mean lower transportation costs and a smaller carbon footprint. It's a win-win. Now, if you take that idea a step further, you get to functionally graded materials, or FGMs. Instead of just a simple mix, an FGM has a smooth, continuous gradient of properties. Imagine a material that's pure ceramic on one side, pure metal on the other, with a seamless blend right through the middle. And this is where the design gets really, really clever. By adjusting the recipe of that blend, what engineers call the power law index, they can precisely control how a beam is going to perform. This means they can design a single piece of material to have the exact amount of stiffness and flexibility needed for any specific job. But what if materials didn't just have to sit there and take it? What if they could actually react? This brings us to the most exciting frontier of all, the smart revolution, where materials become active participants in their own environment. So what makes the material smart? It's that its properties aren't fixed. You can change them on command with some kind of trigger, like an electric field, or heat, or even just physical pressure. They stop being passive structures and start becoming active, responsive systems. Let's meet a few of these incredible materials. First up, you've got piezoelectrics. You've probably used one in a gas grill lighter. You squeeze them, they generate electricity. You apply electricity to them, they change shape. Then there are phase-changed materials like vanadium dioxide, which can flip from being an electrical insulator to a conductor with just a little bit of heat. And finally, you have electroactive polymers, which basically act like artificial muscles, contracting whenever you apply a voltage. So what does all this mean in the real world? It means we can build beams that can sense when they're bending and then actively stiffen themselves up. We can build bridges that harvest energy from the vibrations of traffic. We can even create surfaces that can steer beams of light on command. This is a complete paradigm shift in what engineering can do. All of this really points to one conclusion. The future of engineering and technology isn't just about better design. It's about building with intelligence that's baked directly into the materials themselves. And that intelligence is being forged at the smallest possible scales you can imagine. The next great leap is happening right now at the nanoscale, where we can manipulate the very building blocks of matter itself. In labs today, scientists are engineering materials like graphene to manage heat, quantum dots for hyper-efficient electronics, and even tiny nanorods that can act as phase change materials just to steer light. These aren't just small improvements. These are the fundamental bricks and mortar for all of tomorrow's technology. This quote just perfectly captures the journey we've been on, doesn't it? For millennia, we'd build things to be strong. Now, we're finally learning to build things that are smart. And you know, the most incredible thing is that this is all one unified field of innovation. The same principles that keep a concrete bridge from deflecting are the very same principles, just evolved and miniaturized, that allow a quantum dot to manipulate a beam of light. It really is one continuous journey. So, from the brute strength of steel to the built-in intelligence of a phase-change nanorod, the very substance of our world is being reinvented. This isn't just an improvement, it's a revolution in what we can build, and honestly, in what we can even imagine. Which leaves us with one last, kind of provocative thought. We've explored materials that can react and adapt. The next logical step is materials that can compute, that can even learn. So I'll just leave you with this question. What will we build when our materials can think for themselves?